Well, good afternoon, everybody. My name is Frank Mitloehner, and I'm a professor and air quality specialist in the Department of Animal Science at UC Davis. And the title of my talk today is Rethinking Methane, the Path to Climate Neutrality. I think it's a very important topic, not just because this is my area of work, but because I actually think that methane, among all those greenhouse gases leading to this discussion around climate footprint and carbon footprint and so on, is the Achilles heel of animal agriculture. And so it's a pleasure for me to talk to you about the new things we have learned about methane and what it means in your context. So for those of you who are on Twitter, I am on Twitter as well, and my handle is GHGGuru. My center, the UC Clear Center, is also on Twitter. You see the handle down here. Now, if any of this, what I'm presenting to you here today is going too fast or it's too technical or something, then please know that my center has produced a short video. It's called Rethinking Methane. It's available on YouTube for free. Rethinking Methane, a 5-minute video. I encourage you to watch it and share it. It's really important that we get this information out. So first of all, just a little 101 on what greenhouse gases are, okay? What they are and why they matter. So look at this slide here, and you see on the left side, the sun radiating down solar radiation to the surface of the Earth. That solar radiation is generally just reflected back into space. But I should say, there is a layer of gases that keeps some of that radiant heat from that solar radiation back. And actually traps in. And that layer is consisting of gases called greenhouse gases, including carbon dioxide, CO2, methane, which is CH4, nitrous oxide, N2O, and others. And these greenhouse gases pretty much form a blanket over our atmosphere. Just imagine sitting outside on a cool summer evening and you need a blanket to stay warm. Why do you stay warm? Because that blanket keeps your body temperature, the radiation from your body, close to your body, and that's what keeps you warm. That blanket isolates around you, and that's what these greenhouse gases do. They form a blanket over our atmosphere, keeping the heat from the sun in our atmosphere and preventing us from getting too cold. We would be not able to live on Earth without greenhouse gases. The problem is that blanket is getting too thick because we're putting too many greenhouse gases into the atmosphere. And hence the discussion around one gas in particular, and that's methane. Methane is the main greenhouse gas within animal agriculture. By the way, nitrous oxide is the main greenhouse gas around plant agriculture. I know, of course, you're in the UK, but I'll give you a quick rundown of what greenhouse gas sectors look like in a country like the United States. It's not dissimilar in a country like the UK, by the way. What you see on this slide is the EPA emission inventory for greenhouse gases for the United States. And it shows that there are 3 sectors, namely transportation, power production and use, and industry. These 3 sectors, heavy users of fossil fuels, which are oil, coal, and gas. And these 3 sectors emit approximately 80% of all greenhouse gases, 80 that is, a little bit above that, a little more than that. Contrast that to agriculture. This is a graph depicting agriculture with a cow, but this is not animal agriculture. That's 9%. It's all of agriculture, so animal and plant combined. Animal agriculture alone in the United States amounts to approximately 4% of all greenhouse gases. The difference between 9 and then the 4% for animal agriculture is plant agriculture. So approximately 4% of greenhouse gases in a country like the United States or the UK stem from livestock. But as you well know, there's a lot of discussion as to what the contribution of animal agriculture is on climate. Because what the critics of animal agriculture do is they don't present to the people in your country the greenhouse gases in the UK that stem from animal agriculture, but they always use a global number because the global number sounds more daunting. The global number for livestock producing greenhouse gases is 14.5%. I find it very dishonest for these campaigners not to use the numbers that really matter to the people who live in a certain locality, like UK. But anyhow, that's what they do, and they do it effectively because everybody is reporting on that 14.5% number rather than using UK-specific numbers, which you should insist they do. So why is that number so much lower in the UK compared to the global average? It's so much lower because your animals are so much more efficient. You are so much more sustainable than the global average. And therefore, you deserve to be depicted with the numbers that are associated with what you do. Make sure that happens. What are those greenhouse gases that we are concerned about? Well, there are three here in particular, and that's CO2, then it's methane, and nitrous oxide. As you can see here, methane is a gas that has a higher potency than CO2. And that potency is referred to as the global warming potential, or GWP 100. That's what it's called. The GWP 100 expresses the potency of a gas to trap heat from the sun. Okay, and what this GWP 100 shows is that methane traps the heat from the sun 28 times more than CO2. Nitrous oxide is even more potent in trapping heat. 265 is the factor here. So if you were to run a farm, a ranch, and you produce, let's say, 100 tons of methane, then all that people need to do is multiply the 100 tons times this factor, this GWP factor. So 100 tons times 28. To arrive at the so-called CO2 equivalents. CO2 equivalents. That's what the world has been doing for the last 30 years. Scientists, and particularly scientists from the UK, from Oxford, have questioned that matrix since, the global warming potential. Why? Because in addition to being more potent, methane has other characteristics that have to be considered in order to fairly derive public policy decisions on it. And I will explain that in quite some detail. So how is methane different from the other greenhouse gases? Well, the biggest difference is that CO2 and nitrous oxide are only produced. They are not really destroyed in the atmosphere, but they are produced, whereas methane is both produced and destroyed, and almost at equal rates. It is true that methane is more potent than CO2, but it's also true that methane is not just produced, but also destroyed, which is depicted on the next slide, which shows the global methane budget. On the left side of this graph, you see that there are various sources of methane, including fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so on. These different sources emit a total of 558 teragrams of methane globally. 558. So that's the sources. And this is where most people stop the discussion. But they leave out something really important, namely what I just pointed out, that methane is not just produced, but methane is also destroyed. And you see that on the right side of the graph. There are sinks in the world amounting to taking out 548 teragrams of methane. So in other words, there's a process in the air that takes down methane. And that process is almost as strong as all the emission sources, meaning just like in a normal budget where you have income and expenses, here you have sources, which are emissions of methane, and you have sinks taking methane out of the atmosphere. And if you look at this strong arrow pointing downward, you see underneath sink from chemical reactions in the atmosphere. I don't mean to make this a chemistry lecture here, but it's really important for you to understand this. There's a process in the atmosphere called oxidation. To be precise, it's called hydroxyl oxidation. And what that means is that while a methane molecule is in the air, sooner or later it meets another molecule called a hydroxyl radical. That radical steals away hydrogen from the methane and destroys it. And that, ladies and gentlemen, happens within 10 years. 1 decade, on average, methane is gone. Okay? So that's really important to know. There's a process that destroys methane. It's called oxidation. And that oxidative process takes place within 1 decade after methane is emitted. In other words, if you were to have a dairy, let's say, or a beef operation, and you started that in 1990, then the methane that was belched out or produced from animal manure in 1990 was gone in the year 2000 because it was destroyed. But that methane that was produced in 1990 and destroyed by 2000 is replaced by new methane from those cows, from those cattle in the year 2000. Overall, though, there's no increase in methane. When you have constant cattle herds, the amount of methane produced versus the amount of methane destroyed are in balance. And that is really important, okay? Take none of what I say here as methane doesn't matter. Methane really matters. But the way its impact on climate is depicted is erroneous. This slide here shows another difference across these three greenhouse gases, namely the lifespan of these gases. I already told you that CO2 and nitrous oxide are greenhouse gases with a long lifespan. They're not really destroyed. And as a result, their lifespan in the atmosphere is very long. In the case of CO2, it's 1,000 years. And that's why it's called a long-lived climate pollutant. Methane is a short-lived climate pollutant. And as I just told you, the lifespan of methane is only 10 years. What this here really means is that any time that you have ever burned fossil fuel, for example, by driving a car or heating your home or so, every time you burn fossil fuel, you add new additional CO2 to the atmosphere, which is added to the stuff that you put into the atmosphere yesterday and the day before and the year before and the decade before, and all the CO2 your parents and grandparents and so on put into the atmosphere. That's what makes CO2 a so-called stock gas. Every time we blow out CO2, that comes on top of the existing stock. The same is not true for methane, and that's really important. Methane is a flow gas. It's produced and destroyed. Please remember that. This here is an important slide, particularly for cattle producers of all kinds. It shows the biological or biogenic carbon cycle. And so methane is chemically CH4, and of course it contains carbon, the C in it. Have you ever wondered where that carbon that's in the methane, where that carbon comes from? Well, I take you back to photosynthesis and the question of what plants need to grow. Plants during photosynthesis require three main things. They need sunlight, they need water, and they need a source of carbon. That source of carbon is atmospheric CO2. So plants take CO2 out of the atmosphere and then they produce oxygen and of course carbohydrates. So the carbon in the carbohydrates originated in atmospheric CO2. Okay, that's where that carbon comes from. Now a bovine comes along and eats that carbon, that carbohydrate in other words, and belches out some of that carbon in the form of methane, or it's maybe produced by this animal's manure. That methane is not new carbon to the atmosphere because it's recycled carbon, carbon that originated in the form of CO2, okay? So now that carbon is no longer CO2, it's now methane, and it stays methane for approximately a decade. And within that decade, the process of oxidation takes methane, destroys it, and gets it back to be CO2. That CO2 is then added to the atmospheric pool of carbon, the atmospheric pool of CO2, from which plants can draw again during photosynthesis. So this here is a carbon cycle. And as long as you do not add additional new livestock to your existing herds, you're not adding new additional carbon to the atmosphere. You're recycling existing carbon back and forth from CO2 to methane and back and forth and back and forth. Okay, really important, because here is where livestock is so different from, let's say, fossil fuel sources. How so? Fossil fuels are things such as oil, coal, and gas. And by far, fossil fuels are the main reason why our planet is warming. What are fossil fuels? Well, oil, coal, and gas used to be forests, and they used to be animals millions of years ago. They died, they decayed, fossilized and accumulated in the ground. And over the last 70 years, 70 years, we have extracted about half of all that carbon that accumulated over hundreds of millions of years. We've extracted half of all that carbon from the ground through drilling, through fracking, and so on. And we took that carbon and we burned that carbon when we drove cars, trucks, trains, planes, ships, and so on. And by doing so, we are putting that carbon from the ground into the atmosphere where it accumulates. And remember, it really does accumulate because that carbon, that CO2 carbon, has a lifespan of 1,000 years. That, ladies and gentlemen, is the main culprit for human-caused climate change and not belching cows. Here's a direct contrast of fossil fuel-derived carbon versus biogenic or biological carbon. On the fossil fuel side, you have that carbon that was stored in the ground. We unlock it when we drill it or get it up, extract it, and then it becomes atmospheric CO2. And that accumulates and becomes more and more and more. That's a one-way street. I want to make that very clear. That's a one-way street, not a cycle. On the cow side, you have atmospheric CO2 that makes it during photosynthesis into plants. The plants put a lot of that carbon into the ground, and carbon sequestration occurs, the storing of that or the storage of that carbon in the ground. Some of the carbon, however, remains above ground. The animal eats it and then belches out some methane, as well as the animal's poop will produce some methane. That methane stays in the atmosphere for a decade, is converted back into CO2. That, ladies and gentlemen, is a biological cycle, not dissimilar to the cycle of carbon that's associated with human respiration. Ever wondered why what we respire, that CO2, is not counted as a greenhouse gas in our inventories? The reason why it's not counted is because everybody says we are not adding additional carbon. Well, how so? Because we're eating plants in our diets, and those plants, when they were still alive, had sucked carbon out of the atmosphere during photosynthesis. So that carbon that the plants had taken out of the atmosphere, we now eat and then respire. So it's a wash. But guess what? This is also a wash. As long as we don't grow livestock herds, we are not adding new additional carbon to the atmosphere. But we are currently acting as if methane were not a flow gas, which is produced and destroyed, but we're acting as if methane were only produced, similar to CO2. And that's depicted on this slide. First, I will lead you through how CO2 accumulates in the atmosphere. So imagine you have a job in town and you drive from home to town every day of the week. So on day one, which might be Monday, you drive your car, you put CO2 into the atmosphere. On day two, you drive again, you put the similar amount of CO2 in the atmosphere, which is now on top of what you put out the day prior. And so now you can see you have an additional block there. On Wednesday, you drove to work again, and that's now on top of what Tuesday and Monday's activities amounted to. So you get the gist of it. Every time you burn fossil fuel, you add to the existing stock of carbon in the atmosphere. That, ladies and gentlemen, is why CO2 is referred to as a stock gas. Okay, it's accumulating in the atmosphere. How about methane? Is methane doing the same? Every day that our cows belch, does the same principle occur? The answer is no, it does not. This slide shows it. If you were to have, let's say, a beef operation and you started it in 1950, then in 1950, when you started it, you put new cattle on your operation and they, for the first time ever, produced methane. During that first decade, your operation added new additional methane to the atmosphere. But after that first decade, so from 1960 on, as long as your herd size remained the same, the amount of methane produced and the amount of methane destroyed through hydroxyl oxidation were in balance. So methane, remember that please, methane is not a stock gas, methane is a flow gas. It's both produced and destroyed, and it's keeping in balance as long as herd sizes remain. However, the GWP 100, the global warming potential that's used to look at the importance of methane and nitrous oxide, acts as if methane were a stock gas, as if it were accumulating in the atmosphere, even though it doesn't. The first person who pointed that out was your very own Professor Miles Allen from Oxford University, one of the world's leading experts in climate science. You will find his name mentioned on several of my slides, along with source information for what I'm presenting to you today. So Miles Allen and his team at Oxford Martin have published many papers, peer-reviewed papers, but also relatively non-technical blogs and so on. Some of them you find here. So what they have a beef with is that methane is just simply compared to CO2. They are saying this is inappropriate, and the reason why it's inappropriate is because methane is not just produced, methane is produced and destroyed, and we have to account for that. Otherwise, we tell an incorrect story. So the scientists from Oxford Martin say publicly that if you have a constant livestock herd, then the GWP 100 that's currently being used to quantify your impacts is off by a factor of 4 times higher than it actually is. 4 times higher than it actually is. I will now lead you through 3 scenarios, and I show you how the current GWP 100 depicts these 3 scenarios, and how a new unit called GWP star that came from Oxford sets the record straight and makes this discussion one that's based in science and not fiction. 3 scenarios. The first one, the top one, is a warming scenario by which over 30 years, methane increases by 35%. So that's a strong increase of methane over 30 years. The second scenario will be a slight decrease of methane, but we call it stable. Slight decrease by maybe 10% over 30 years though. And the third scenario is one by which we reduce methane. That could be in the form of using feed additives or manure treatments and so on. We reduce methane in this third scenario by 35% over 30 years. So if you were to depict these 3 scenarios using GWP 100, then that would look the following way. If you increase methane by 35%, GWP 100 would predict a very strong increase in greenhouse gases. Even if you have stable methane though, GWP 100 predicts less, but still a very strong increase of greenhouse gases. But if you decrease methane by 35%, GWP 100 still predicts a strong increase of greenhouse gases. Again, GWP 100 treats methane as if it were a stock gas, as if it were to accumulate. Even under stable conditions and under decreasing conditions, GWP 100 predicts that greenhouse gases go up, that warming goes up, even under stable and decreasing methane emissions. So as I told you, Miles Allen and colleagues have said this is not appropriate. If we have stable conditions for methane, then the amount of methane produced and the amount of methane destroyed are in balance, meaning no additional warming. And if methane decreases, something miraculous will happen. And here is what this new unit GWP 100 predicts. GWP 100 predicts that if you increase methane by 35%, then indeed the warming equivalent goes up, similar to what GWP 100 predicts. If you hold methane stable, however, then you don't see any additional warming. If you decrease methane, then you get negative warming. And negative warming means cooling. So GWP 100 versus GWP star are not just different, but the unit, the sign changes from positive emissions to negative emissions. And that's a huge opportunity to you, because if you reduce methane, then you help cool the planet. How exciting is that? This slide here, one of my last ones, shows how increasing CO2 and increasing methane from whatever source affect the related warming. An increasing amount of CO2 put into the air will lead to a strong exponential increase of the related warming. an increasing amount of methane will lead to a similar increase in the related warming. However, constant emissions of both CO2 and methane lead to still increasing amounts of CO2 because it's a cumulative gas, a stock gas, whereas constant emissions of methane lead to no further increase in warming. And that, ladies and gentlemen, is what we have proposed with the Paris Climate Accord, namely limiting our global warming to less than 1.5 degrees. We can achieve that for the livestock sector with stable methane emissions. So a stable herd will lead us there. But now let's see what happens if we reduce both CO2 and methane. What happens to the related warming? If we reduce CO2, then the warming associated with that CO2 will still go up, even though we're reducing CO2, up until the point that we are at net zero emissions of CO2. Once we have net zero for CO2, then the warming of CO2 stops. That's what it takes. Net zero is what it takes to plateau the warming related with that CO2. Look what happens, however, if you decrease methane. If you decrease methane, you have an instantaneous reduction of warming, meaning a cooling effect. And that's a beautiful thing. And that is what makes methane not a super pollutant, but CO2 a super pollutant, because even if you reduce CO2, the warming goes up. So that is what makes CO2 so dangerous. And that is also what makes methane not a super pollutant, but a super opportunity, because if we reduce it, then beautiful things happen. Can that be done will be the question that you might ask. We have a new law here in California that mandates a 40% reduction of methane to be achieved by the year 2030. At first, our dairies and our feedlots and ranchers went wild. They thought this could never be achieved until they learned that the state of California will not just shove this regulation down these producers' throats, but instead use an incentive approach to get the job done. The state of California poured a lot of money into methane mitigation, and the livestock sector matched that. They put technologies such as anaerobic digested, or in this case, covered lagoons on their operation, trapping biogas. They're incentivizing the use of feed additives to reduce enteric methane, methane that's belched out. We have already achieved a 2.2 million metric ton reduction of methane annually through the use of methane reducing techniques and technologies, and through the state of California working collaboratively with our livestock producers. We have already reduced methane from our livestock sector by 25%. I told you we have a 40% goal, which has to be achieved 10 years from now. Now we are already at 25%. We are over halfway where we need to go. Why does that make me excited? It makes me excited because when we manage to reduce methane, then that leads to a relative cooling effect for methane. And that relative cooling effect for methane counteracts nitrous oxide that a beef operation, a dairy operation also emits, compensating for that, okay? So the methane reduction will compensate for some of the warming from other processes, overall leading to a path of climate neutrality. We can achieve climate neutrality in animal agriculture. We are well on our way of being there very soon here in California. We will share this information with other states and countries, and I'm very optimistic that our livestock sector will become climate neutral in the years to come. So I hope, in closing, that you view methane, like I do, not so much as a challenge as viewing it as an opportunity, okay? So with that, I want to leave you with my information, the address for a blog that I write frequently, and also let you know that the CLEAR Center, which I'm the director of here at UC Davis, has a webpage that you find on this slide. I thank you so much for your attention, and I hope that you have a great rest of your meeting. And of course, I'm looking forward to answering any questions that you might have. Thank you very much.